Hey there, here is another episode of Maths with a Black Rat. In this video, I want to talk about variance and standard deviation, and this is the world of data, not the world of probability distributions. This is data world, like you've gone out and measured a bunch of data points and now you have to analyze it and figure out how to interpret it. Okay, so variance and standard deviation are measures of spread. Spread means how far flung your data is. In GCSE, we learn about range as a measure of spread. That's your biggest point minus your littlest point, and that's a pretty chunky measure of spread. We also learn about interquartile range, which is like the middle 50% of your data, which gives you what the middle bulk is doing. That's another idea of spread. Variance and standard deviation is another way, again, to talk about spread. So the idea here, the definition really starts with variance, that it's the mean squared distance from the mean. That sounds like a bit of one of those cryptic Zen things to meditate on. Okay, we'll talk it all through. What it's about is I want to know how far a typical data point is from the mean of all my data points. And the standard deviation is that number, but variance is nicer to talk about. Okay, here's the whole shebang. Here's an example. So here's 5 data points that I just made up, and I picked 5 of them because it saves us from pages and pages of tedious arithmetic. It's enough to give the idea. Okay, so suppose you've got 5 data points, and n is how we keep track of how many we have. N equals 5. Okay. When I write x sub I mean one of my data points, where I tells me who I am. So that's x sub 1, that's x sub 2, x sub 3, x sub 4, x sub 5. So x sub I is just a generic one in the middle. Okay, so my i's go from 1 all the way up to n. That's how we do the notation. Okay. So if I want the mean of these 5 numbers, well, we add them up and divide by how many we have. And if you should pause the video and make sure that my math is correct. Okay, you should come out with 4.8, and we call that x bar. X bar is the notation we use to indicate the mean of our data set. In probability world, we use the Greek letter mu, but we're in data world, so we'll use x bar. Okay, that should be okay. If I want to think about the average distance from the mean, that concept, okay, the average distance from the mean, well, my mean comes in at 4.8, which is about here. Thinking of my data in order. Yeah, 4.8 is about here. And I know that 9 is kind of far away. Each of the 5s are fairly close. 3 is a little bit away, and 2 is a little bit more away. And I want to know, what the average distance is. Because you could hit a mean of 4.8 if you take this 2 and drop them down to a 0 and take that 9 and bump them up to an 11. You'll still come out with a mean of 4.8, but now my data is more spread out. So I really want to know how far how far a typical point is from the mean, because that's an idea of tightness. Okay, so one way you could think about that is to do a straight up subtraction. My mean subtract a data point. But I know that some of my data points are less than the mean and some of the data points are greater than the mean, so that's going to come out positive for some data points and negative for others. And if you were in the situation where you had a 2, a 5, and an 8, and that was your data, so 5 is your mean, that's 3 below and that's 3 above, and if you took the average, your average distance would be 0, and that doesn't make any sense. So I don't want the 3 and the negative 3. I want the fact that I am actually 3 units away and another 3 units away, so the average distance away is 3. That's a very simple example. So I don't want just the subtraction. I want the absolute value, the modulus of that distance. And it turns out that you can use this, but it's a complete pain for doing arithmetic with. Modulus is a real tedium for arithmetic and algebra and all the nice rules we have of algebra. And another way of dealing with negatives, you know, if you're doing a subtraction and you really don't want a negative result, another thing you can do is to square it. And that's what we end up doing for variance. That's what we mean by the squared distance. The squared distance from the mean. The squared distance from the mean. And that square just deals with negatives. And it turns out to be really nice algebraically and super pretty when you get into probability distribution world. This is just a really useful way to do it. You're going to have to take that on faith at the moment. Okay, but this is how we go. Okay, so if I want the average of all those little distances, I'm looking at a calculation like this. So here's the mean of 4.8, and my first data point is a 2, so there's the distance between them, and I square it. Then I do it for the next data point, so 4.8 subtract 3, quantity squared. My next data point, and you should do this along with me. Don't just let me do the writing. You do it out. Okay, so there's my 5 data points. The distances from the mean, and I've squared to get rid of any negatives. And then if I want the average of that, I want the mean. That's a particular average. I want the mean of that, so I'm going to divide by 5. And that calculation, which is a lot to write out, will shake out as 28.8 over 5, which is 5.76. And that's the variance for my data set. And if I want the standard deviation, that's Elizabeth abbreviation, but useful. The standard deviation is going to be the square root of that number, which will shake out as 2.4. So on average, a typical data point is 2.4 units away from the mean. I'll say that again. You should write it down. The standard deviation is saying that a typical distance of a data point from your mean is 2.4. Okay. If you have a small standard deviation, it means your data points are quite close to your mean. If you have a huge standard deviation, it means that a typical distance is big, so your data points are really, far flung. I hope that makes sense. If that doesn't make sense, drop me a note. All right, so from here, I want to make a note about squaring to undo the variance. And I haven't written out the formal formula for you. All right, let's do this. Fresh sheet of paper. Okay, so in general, okay, the formula for variance looks like this. Take the distance from the mean, square it, add up all those little bits from your first data point to your nth data point, divide it by how many you have, so that gives you the mean of squared distance from the mean. That's what I meant with my first sentence. Okay, so another way that you can do the same calculation is by this pattern. I'll write it out and then I'll talk you through it. Okay, this calculation, I know it looks horrific when you first start, but when you get used to it, it's fairly friendly. This expression is exactly the same as that expression. And it turns out that this is easier to do calculations by hand with if you have to, do it by hand. These days we would use a spreadsheet or some statistical package to help us because arithmetic is tedious. But this is friendlier to work with than that is, and exam questions tend to be based around this format as a way of testing you to see if you understand the pieces involved and how they all fit together. Okay, so what this is saying is, okay, divide by n, we're taking a mean. This is the mean. Okay, we're adding things up. We're adding up our data points squared. So you take each of your data points and you square them, then you add all that up, then you divide by how many you have. So this portion is the mean of the squares. We'll do an example with numbers. Okay, I'm just showing you the formula. Okay, this is the mean of the squares, and this is the square of the mean. If I add up my data points and divide by how many I have, that's the mean. So I'm taking the mean, x bar, and I'm squaring it. So this is the square of the mean. Write it so you can read it. The square of the mean. And I remember this phrase because it has a really nice rhythm to it. The mean of the squares minus the square of the mean. And that's what variance is. And this pattern is used in probability distribution world, so it's worth getting comfortable with it now. Excuse me. Okay, so with our numbers, the way that we'd mess with this is we'd say, okay, so we have our 2, our 3, our 5, and our 9. That was the data we started with. Okay. Well, I can get my hands on x bar. That's him, the mean, okay. Add them up and divide by, and that came out as 4.8. We did that previously. Okay. And if I take the square of that number, and I don't care about doing it in your head or by hand, you'll get 23.04. Okay. But I also need to look at squaring all the numbers and adding that up and dividing by 5. Okay. So once I found x bar and x bar squared, the square of the mean, okay, then I'm going to write out my data points again, but with each number squared. So that's going to be 4, 9, 25, 25, 81. So the sum of all those numbers squared is 4 plus 9 plus 25 plus 25 plus 81, which I did write down and I've just managed to lose. You should get if you do that. My goodness. All right, well, we'll have to do it out together because I lost the sheet that I wrote it down on. I've only got a small desk. We'll do it together. So 4 plus 9 plus 25 plus 25 plus 81 gives you 144. That's tidy. Okay, but I need to divide that number by n, so that's the average of the squares, the mean of the squares if you like. So 144 divided by 5 will give you 28.8. I hope you're doing this along with me. Okay, so variance is going to be the mean of the squares minus the square of the mean, which is 28.8 minus 23.04, and that should come out as 5.76, which is the number we found before for variance. This is much nicer. Statistics packages will give you, typically, they'll say something like the summation of your data points turns out to be 24, and the summation of the squares of all your data points turns out to be 144, and then the exam question will say, okay, you work out variance and standard deviation. And you're like, okay, well, that shows me where to drop the pieces in. Okay. We know that x bar is the summation of our data points divided by n squared, and that piece stays as it is. So the summation of our xi's is 24. That number right there is 24. And the summation of our data point squared is 144. So that piece right there is 144. You have to drop in n, which here is 5. And you have to remember to square that bit. But you just take what the exam question gives you, plop, plop, insert, 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 click, click, click on the calculator, and out comes your variance. I'll do another example with you. And before I do another example, I do want to show you why this algebra works. And having said that out loud, I think I'm going to do another numerical example, and then I'll show you the algebra at the end. I think that makes more sense. Okay, so here's another example I made up to play with. So suppose, okay, that you have a statistical package, a stats package on the computer, so it's some software. And suppose you've tapped in a whole bunch of data points. And this is example, suppose you have 15. That's not too icky to do by hand, but just to, give you an example. Okay, so you've got 15 data points. You typed it into your stats package, and your stats package told you that the summation of all your data points shakes out as 291. And the summation of the squares of your data points shakes out as 6,207. And you have to figure out the variance and the standard deviation. Okay, so we use, just like I've been saying, variance is, and I really like to write out the words. It's the mean of the squares minus the square of the mean. Isn't that a nice rhythm? The mean of the squares subtract the square of the mean. The mean of the squares, the mean of the squares, the mean of the squares, there we are. Subtract the square of the mean. There's the mean, that's x bar squared. The mean of the square is the square of the mean. Okay, so again, that piece, add up all your data points and get 291. That right there is going to be 291. And the sum of your data points squared is 6207. So this piece right here is 6207. We know that n is 15. Remember to square that bit. We're off and away. So 6207 divided by 15, subtract 291 divided by 15, that fraction squared. If you do that out, you should get, check your work, 413.8 subtract 376.36. I did this ahead of time, you should check. And that should shake out as 37.44. And that's your variance. And your standard deviation is the square root of that number. The square root of the variance, so the square root of 37.44, which you should check is 6.1 to 1 decimal place. I suppose your question would tell you how many decimal places to use, or maybe your teacher has a standard. So that's a good question to ask, how many decimal places you need to write down. Here I've just done 1 decimal place. Okay, so that's a typical exam question. That's how you shake it out. If you want to verify, if you want to verify that this formula is the same thing as the definition of variance, which was the average distance squared from your mean, you can do this through for all your data points. These are the data points I used. 10, 11, 11, 14, 15, 15, 17, 21, 24, 24, 24, 25, 26, 26, 28. Okay, so I just pulled these numbers out of the air. I wrote 15 of them, so it wasn't too arduous to do the arithmetic by hand. So if you physically add all these numbers up, and they should sum up to 291, because that's what I told you here. So if you add all these numbers up, you should get 291. And if you square all these numbers and add those up, so 100 plus 121 plus 121 plus, I've forgotten what that is, plus, that's 289, isn't it? Plus 225 plus blah, 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 you should come up with 6,207. And if you do it all out by hand by saying, okay, so your mean, the mean worked out as 291 over 15. Oops, there goes my calculator. 291 over 15, which is 19.4. Okay, this is just so you feel confident that all the methods are the same and that it works. I don't think they'll ask you to do this out by hand on an exam question, but it's nice to sandbox it in your own time. Okay, so if you take each of your data points, whoops, the mean, subtract your data points, and add all those little bits up. So you go 19.4 minus 10 and square it, and then 19.4 minus 11 and then square it, and you do this all the way down to the very last one, 19.4 minus 28, and you square it. Then you divide it by 15 because that's how many we have. If you go through that, you should come up with 37.44 because it's all the same. This is bonus for your own reassurance. This is how an exam question would go. I hope that's clear. The last bit I wanted to do is to show you algebraically why, sorry, my camera's not very big, to show you why this formula and this formula are the same. So let's look at that. Okay, so here's how it goes. So here's the definition. A variance. You've got n data points. Your mean, subtract each data point squared divided by n data points. Okay, so if I multiply out the brackets in that summation, and I'm going to drop the indices for simplicity, but we know that they're there. Okay, so if I multiply out these brackets, that's going to give me the mean squared minus 2 copies of the mean times our xi plus our xi squared, and I'm still dividing by n. So that's just multiplying out the brackets. And when you're doing a summation of things that are added or subtracted together, you can break those summations up like this. Well, I suppose I'll write it as a subtraction. Do you want to add a negative or subtract the positive? We'll take that as a subtraction. And again, you should do this yourself to be comfortable with what I'm writing. Okay, so I've broken this into 3 separate summations and then into 3 separate fractions. If you're not happy with that step, drop me a note. Okay, so now I'm going to look at what each of these pieces is saying to me. So I know that my I'm adding up from I equals 1 to n. I is the incrementation, the moving bit, but this is a constant. X bar, my mean, doesn't depend on, I mean, as I increment I equals 1, I equals 2, I equals 3, that's just the same thing. So if I'm adding up, well, I'm writing it out n times, and that's going to give me n copies of my mean squared, and I'm still dividing by n. And here, this is saying, okay, so x sub I is the moving piece. So when I equals 1, I'll have 2x bar times x1. And then I'll add 2x bar times x2. And then I'll add 2x bar times x3. So every term in this sum has that multiplied against it. I could factorize it out and say this. And this last piece I really can't do anything with because my index goes from I equals 1 to n, and every time that I increments, that piece changes. So there's no further way to simplify that piece, so he just stays as he is. From here, my n's will divide out on the first piece, and that will just give me x bar. You know what, I'm just going to stick them in brackets because the squared is outside the bar. So x bar, the mean, squared. And what's happening over here? Well, I've got 2x bar, and then I can identify that piece. This piece is saying add up all your data points and then divide by how many you have. That's what x bar is. Add all the data points up, divide by how many you have. That's the mean. That's x bar. And then this last piece just hangs around, like I said. Now this is interesting because I've got one copy of the mean squared, and here I've got 2 copies of the mean squared. So that gives me minus 1 copy of the mean squared. Then I've got that piece, and if you reverse the subtraction, we're home. Okay. Sorry, that's gone off camera. And it's perfectly fine to write that bit as x bar, and that bit, showing our x sub I data points, or if you don't like that, you can put him back into that expression. Whatever makes you happy. Remembering that it's the mean squared. Okay, so either of those is okay, and that's the algebraic proof. So just to recap, that's your definition of variance. It's the average squared distance from the mean. And it is also the mean of the squares minus the square of the mean. Okay, that's a long video. I hope it was understandable, and please yell if anything's wobbly. Okay, thanks for listening.